Math 2414, Other Convergence Test, Video 3, P-Series. This is actually a consequence of the integral test, as we're going to see in a moment. But first, let's define what we mean by P-series. And by the way, the P in series for the word power. So the P is going to represent a power. Let P be any real number, so it can be positive, negative, or zero. A series of the form, the sum from n equals 1 to infinity of 1 over n to the p power is called a P-series. So for example, if p was equal to 2, we would have the sum of n equals 1 to infinity of 1 over n squared. And as we saw in the example in the previous video, this converges by the integral test. So we don't have to redo all that, but if you wanted to, you could. But what if p was equal to, let's see, what if p was equal to, sorry, I got something popping up accidentally, there we go. What if p was equal to 1? Then we would have the sum of n equals 1 to infinity of 1 over n to the first power, but why write the 1? But we know that diverges because it's harmonic, the harmonic series. Specifically, it's a harmonic series because if we take the reciprocal of its terms, we get an arithmetic series, or arithmetic series or sequence, depending on if you look at it as a sum or not. But what if p was any power? Can we draw a generalization about a p-series convergence or divergence based solely on what the power is? And we've already got two examples. When p is 2, the p-series converges by the integral test. When p is 1, it diverges because it is a harmonic series. Before we move forward, let's just make a really quick note that if we make the function based on the argument of the sum, 1 over x to the p, and we think about this on the interval 1 to infinity, that will be positive, should be fairly evident. Will it be decreasing? It depends on the power. Will it be continuous? Well, the only place it's not continuous is 0. So let's work on the premise that everything is good for the integral test. Actually, let's not work on that premise yet. Let's analyze when this is increasing or decreasing. Let's start with if p is less than 0. Then the sum of 1 over n to the p, and I'm going to leave off the 1 to infinity, we're assuming it's there. The sum of 1 over n to the p power would equal the sum of n to the negative p power, but negative p would be greater than 0 because p is less than 0, so it's negative, is the opposite is positive. Well, if that power is positive, then the limit as n approaches infinity of n to the negative p would be infinity because the power is positive, and if you raise a larger and larger number to a positive power, it continues to become infinitely large. This is like when we analyzed the r to the n when we did geometric series, that anytime you raise a number to a positive power and that base keeps getting larger, so does the value. So therefore, we know that the series 1 over n to the p diverges by the test for divergence. Remember, the test for divergence says if the individual term, not the sum, but if the individual term limit does not go to 0, this one clearly doesn't go to 0. It goes to infinity. If your n term doesn't go to 0, then your series instantly diverges. End of story. So we already have a classification for p series when the p is negative. So let's talk about when it's positive. Now, if the p is 0, let's go ahead and handle that case. If p equals 0, then n to the p power is equal to 1 on 1 to infinity. The only place we would have an issue is n was also 0, but 0 is not included in our interval for n. So therefore, the sum of 1 over n to the p would be the sum of 1 over 1, which is the sum of 1. But remember, we're going from n equals 1 to infinity. And there's no n. So for every value of n, we would just get 1. So n equals 1, that's what we're adding. N equals 2, that's what we're adding. N equals 3, n equals 4, dot, 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 dot. And this clearly diverges. Adding a bunch of 1s will not settle down to get closer to infinity. So when p is 0, we have divergence. And when p is less than 0, we have divergence. So now we have to do is analyze what happens when p is positive. And as you should already be able to deduce, we can't just make a generalization when p is positive, because when p was positive 1, we got divergence, and when p was positive 2, we got convergence. So what we're going to do, and you may have seen it as I scroll through page 2, which I already had set up. What we're going to do is we're going to, well, let's think about what happens when p is positive. Our function, which is currently in pink, is positive still, but it should be evidently decreasing, because if the p is a positive number, then being a positive exponent, it does not ship it upstairs, so it stays in the denominator. And so as the x gets larger, the denominator gets larger, the fraction collapses to 0. This thing is decreasing. You could also check the derivative, but trust me on this one. When the p is positive, this function is continuous, positive, and decreasing on this infinity, which means we can use the integral test. So let's use the integral test. And remember, we're assuming that p is positive. We've already deduced what happens in the other cases. So let's integrate 1 to infinity, 1 over x to the p. So we'll replace the upper limit with the t. Integrate from 1 to t. I'm going to go ahead and rewrite it as x to the negative p power, because that's how we integrate this thing. So we would have the limit as t approaches infinity of, well, here we have to be careful. I was going to say we have to be careful because if p is equal to 1, we wouldn't integrate it using a power rule. In other words, if we were integrating this isn't how we would do it. We would just say natural log. But we've already figured out what happens when p equals 1. It was a harmonic series. So we can also assume that p is not equal to 1. We've already figured out that case. And again, because if we were to do what we do when we integrate a power, you would add 1 to the power, so negative p plus 1, multiply by the reciprocal of that, negative 1 over p plus 1. And we're evaluating this from x equals 1 to x equals p. If p were 1, then we would have a problem down there. But we're pretending p is not 1. We've already figured that out. All right, so let's substitute the limits of integration, and then we'll think about the limit. Limit as t approaches infinity, 1 over negative p plus 1, t to the negative p plus 1. And then we don't need the limit on the second half because the lower limit doesn't involve t. If we just put in 1 for the x, we get that. Well, we're checking for convergence or divergence, so I'm not really worried about the tail end of this because that's going to convert. That's equal to something. It's equal to 1 over negative, well, minus 1 over negative p plus 1 because 1 to any power is equal to 1. So that part isn't going to determine convergence or divergence. It's going to be the limit that determines convergence or divergence. So let's think about what's going to happen over here in this limit as the t gets larger and larger. This t currently has a power. So what's going to happen to this limit depends upon whether that power is positive or negative. Specifically, if the thing that's in the pink oval right there is positive, that's positive, then we will have infinity to a positive power, which is infinity. But if it's negative, that exponent is negative, it's going to shift that infinity back downstairs, and my fraction is going to collapse to 0. So let's get rid of this over here by erasing and make note of what we just said. In fact, I think I'm going to type this. If negative p plus 1 is greater than 0, then that means we get infinity to a positive power. The limit diverges to infinity. But if that power, negative p plus 1, is less than 0, in other words, if the original positive power, once it has a negative stuck on it, and I add 1 to it, it stays negative. Because remember, we're looking at the case where p is greater than 0. In the case where p is greater than 0. If our positive number, which becomes negative after we stick the minus in front of it, and add 1 to it, becomes positive, then the limit diverges to infinity. If our positive number gets negated, then added 1 to it because of the integral rule, but it stays negative, then that means that the t would get shipped back downstairs into the denominator before it exploded to infinity. So if we have a denominator exploding to infinity and the numerator is staying static, what does that mean? That means that the fraction converges to 0. Then the limit. All right, so in other words, we get convergence when negative p plus 1 is less than 0. We get divergence when negative p plus 1 is greater than 0. So if we were to solve those, if we were to solve negative p plus 1, come on, draw it, please. If we were to solve negative p plus 1 greater than 0, we could subtract once from both sides and then multiply both sides by negative 1, and that would give us p is less than 1. That gives us divergence. But if negative p plus 1 is greater than 0, this implies that p is greater than 1, and that's the case that gave us convergence. And that makes sense that at 1 we expect a divergence. So now we even know that that's where the p series switches from divergence to convergence. So what does all this mean? Well, if we put it all together, when p was negative, we got divergence. When p was 0, we got divergence. When p was less than 1, we got divergence. When p is equal to 1, we get divergence. So we got a lot of divergence. But once p gets bigger than 1, we get convergence. And so now we have a complete categorization of when p-series converge or diverge. So if you were just waiting for the end result, here it comes. Series, sum 1 over n to the p power, n equals 1 to infinity, diverges. If p is less than or equal to 1, when it was equal to 1, we got the harmonic series, and converges if p is greater than 1. So that's all you really need. You have a p series, meaning that you have n to a power in a denominator, and you get divergence if that power is less than or equal to 1. Otherwise, you get convergence. So the end result's actually pretty easy. We'll take a look at 2 real quick examples. For example, let's say we have the sum of 1 over the square root of n equals 1 to infinity. This is kind of a p-series in disguise, because we could rewrite the square root as a 1/2 power. It's a 1/2. So this is a p-series, power series. Although I don't like using that phrase because that means something a little bit different. It's a p-series with p equal to 1/2, which is less than or equal to 1. Therefore, instantly we get divergence. Diverges. By comparison, kind of a joke in there, you don't know. If we had something like the sum of n equals 1 to infinity of 2/5 times the cube root of n to the 4th power, something messier like that. Well, first off, we have a theorem that says if there's a constant factor on the argument, you can pull it out. So we can pull the 2/5 out. And we can rewrite the cube root of n to the 4th as n to the 4/3 power. So this is a multiple of the p series, and we had a theorem that says series without the constant in front will converge if and only if the series with the constant will converge. So convergence now hinges on this P series, and this is a P series with P equal to 4/3 is greater than 1, therefore converges. So it's a lot of work leading up to the technique, but the technique itself is easy to use. If you are the sum of the reciprocal of a power, you can have some constant factors like we have the 2 and the 5. But if you're the sum of the reciprocal of a power, then your convergence hinges completely on whether the power is greater than 1 or less than or equal to 1. Greater than 1 is convergence. Less than or equal to 1 is divergence.